Welcome to Homework Lib.
In this question, we are given information about a rotational energy transition for a molecule, as well as its vibrational energy transition. And we are asked to find the force constant of this molecule. So the first thing to do is deal with this rotational energy transition from L equals 2 to L equals 1. And our equation for this is E sub L equals L times the quantity L plus 1 times h bar over 2I. And now the moment of inertia for a diatomic molecule is equal to its reduced mass times R naught squared, where the separation between the atoms is R naught. So that's going to be the 0.8860 nanometers given in the problem. And quick reminder of what reduced mass means, even though we're not going to need to substitute for it. In fact, we're going to eliminate it as a variable. It's the product of the atomic masses plus the sum of their masses. Great. So now we need to calculate E2 and E1. And then their difference is going to be the 8.841 times 10 to the minus 4 electron volts. So E2 becomes 2 times 2 plus 1 times h bar over 2I. Notice that my 2 here and my 2 here cancel. So I just have 3 h bar over I. And then E1 is going to be 1 times 1 plus 1 times h bar over 2I. And again, the 1 plus 1 is going to cancel with the 2 in the denominator, leave me with simply, not h bar squared. It is h bar squared. My apologies, I missed the squared there. H bar squared over I. And now I can find, I'm going to call it delta ER for rotation. E2 minus E1 will be 3 h bar squared over I minus h bar squared over I, which leaves me with just 2 h bar squared over I. But like I said, we'll go ahead and substitute mr times r naught squared at this point. Swell. Our next step is to then take a look at the relationship for the vibrational transition. So that vibrational transition is given by delta E equals h bar times the square root of K prime, that's going to be our molecular force constant, divided by the reduced mass. So I'm going to go ahead and square both sides. And delta E squared equals h bar squared times K prime over mr. And I'm going to go ahead and solve both of these equations for mr, just because that will make like I said, we're going to eliminate it as a variable, and then we will be able to set them equal to each other to solve for K prime. So from our vibrational relationship, mr will be equal to h bar squared times K prime divided by the delta E for the vibrational state, squared. And then from our rotational information, mr will be equal to 2 h bar squared divided by delta ER times R naught squared. So let's go ahead and equate those two, and then we'll be ready to substitute. So I'm going to say, we'll be clever. We'll keep color coding just a little bit. So h bar squared times k prime over delta E squared equals 2 h bar squared over delta ER times R naught squared. And as you can see, those h bar squareds cancel. Excuse me. And I'm left with k prime equals 2 times the vibrational energy difference squared divided by the rotational energy difference times the atomic separation squared. So now we're ready to substitute, but we need to convert those two energies in electron volts into joules first. All right, so that 8.841 times 10 to the minus 4th electron volts, we need to multiply by 1.602 times 10 to the minus 19th joules per electron volt. And that gives me an energy of 1.416 times 10 to the minus 22nd joules. And then our 0.2560 electron volts for the vibrational energy difference. Again, multiplying by 0.602 times 10 to the minus 19th joules per electron volt gives me 4.101 times 10 to the minus 20th joules. So I confessed when I first solved this, I didn't do this conversion. And then I got a force constant on the order of 10 to the 20th newtons per meter, which seems pretty extreme. And it's because I didn't do this conversion. So now we can plug in 2 times the 4.101 times 10 to the minus 20th squared divided by the rotational energy difference, 1.416 times 10 to the minus 22nd. And then our separation of the atoms was 0.8860. We need it in meters, so times 10 to the minus 9th, and then we square that. And that gives me 30.26, keeping with 4 significant figures, newtons per meter, which is much more reasonable.